Welcome to the Consulting Specifying Engineer webcast, Evolution of Power Factor Correction in Low Voltage Distribution Networks, sponsored by Schneider Electric. I'm your moderator, Amara Rozgus, and I'm happy to join you today on behalf of Consulting Specifying Engineer and CFE Media and Technology. Here are some tips to get the most from today's webcast. If you're having issue with your slides or with the audio, please refresh your browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume by adjusting the volume on your own computer or by adjusting it on this webcast platform. If you're having technical problems with audio or the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks before contacting an online technician. If you do need a technician, type a message in the Ask a Question box. Individual user questions will be answered in the Answered Questions box. Type questions for our speaker in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the prepared presentation. Today's webcast is being recorded, and you'll receive an email within a week to a link with the on-demand version of this event. To download a certificate of completion and a PDF copy of this presentation, use the Event Resources tab on the left side of your screen. These documents will also be available with the on-demand version of this presentation. I'm happy to introduce today's speaker, Remy Bolduc. Remy is a product application engineer for digital power at Schneider Electric. He started his career with the Hydro-Quebec utility in service and maintenance of high-voltage switchgear, followed by 6 years with S&C Electric in applications of medium-voltage switchgear. For the past more than 20 years, he has held various technical and commercial roles for Schneider Electric, where he has specialized in power quality correction. Remy has presented before, so it's a great pleasure to have you back. Let's begin, Remy.
Thank you very much, Amara. Well, thank you very much for everyone for taking the time to listen to me. It is much appreciated. So today, learning objective, we'll learn what power factor correction is and its benefit. We'll review and understand various low voltage power factor correction techniques. Learn to apply PFC in complex application, and understand how electronic VAR compensator can be used to correct PF. It's kind of where power factor correction is heading in low voltage correction, kind of mimicking of what's been done in medium voltage for large distribution network and so forth. So power factor, it's part of many power quality problems that encompass, the power quality world. Obviously, there is harmonic issues, phase unbalance issue, under voltage, over voltage, voltage notching, over voltage transient, and flicker. Today, we'll touch on power factor, obviously, but we also touch on harmonics and flicker in advanced solutions. So, all of us know the power triangle, but that's where power factor begins. It's a simple ratio of real power over apparent power. And what creates the displacement between real power and apparent power is reactive power. In most network, there's a lagging power factor, and it's created by inductive reactive load. And the most common one found in our network is induction motor. Induction motor, obviously, as the shaft turns, drive the load, generates kilowatt. But in order to do its work, it needs to create a magnetic field internally, and that's what demands reactive power or reactive current. And what needs to be supplied by the power source? Well, it's the apparent power. Sorry. A little bit of adjustment, sorry. Okay. So here we have an example, and we can see how, when you have a power factor of unity, which when the kilowatts are equal to KVA, you basically have your best transmission capability in your network, where there is no waste, let's say, current being transmitted. But when you have a poor power factor, you need to transmit additional current to transmit the same power through your network. The three loads on the top right, well, that's what makes our network. We have resistive load where, the current is in phase with the voltage. When you have an inductive load, purely inductive load, well, the current lags the voltage. And when you have a purely capacitive load, well, the current leads the voltage. So obviously to cancel inductive or capacitive load, you can use capacitor or inductor. And that's what we do when we correct power factor. So another thing that's interesting is that utilities today, they bill us on displacement power factor, which is equal to the cosine phi of the angle between your real power and apparent power. And it's also the ratio of kilowatt over kVA or megawatts over kVA. But with advancement of metering, more and more what we see is another power factor indication referred to as total power factor or true power factor. And to obtain total power factor, well, you include a distortion factor. The distortion factor, in fact, is due to the amount of high frequency current referred to as harmonic that flows in our network, which create a further displacement on the power factor. So that's let's say, the true view of the power factor on the network. So you multiply your displacement power factor times the distortion factor, that will give you the total power factor on the network. To understand this a little bit better, I got an example. On the left, you have a 6-pulse pulse width modulated variable frequency drive. As an example, as a load. The displacement power factor is very good on these drives, typically between 95 to 98% lagging. On the left, this drive doesn't have a line reactor or a DC bus choke, and that yields like a total harmonic distortion in current of 100%, so very, very high distortion. So to calculate your total power factor, well, you have your 0.95 displacement power factor times your distortion factor, which is equal at 0.707. It gives you a total power factor of 0.672. And on the right, you have the same drive, except we added line reactor or DC bus choke, which is always a good practice with variable frequency drive. And the total power factor then, about the THDI dropped to 40%. Total power factor increases because the distortion factor is not as severe. And then we will see a total power factor of 0.882. One thing to note for sure, when you see big discrepancy between displacement power factor and total power factor, that's because you have harmonic in your network. So looking at, why should you consider correcting power factor in any network, high voltage, medium voltage, low voltage, it doesn't matter. The first benefit that customers think about when correcting power factor is that it reduces their utility bills. It's not all utilities, but most utility, in fact, have two charges on their bill. You would have consumption, kilowatt hours, that we all see in our homes, but industry is a little bit different. You would have consumption, and you also have transmission charges and demand charges. And that's typically billed per KVA, dollar per KVA or KVAR hours. And what your power factor should be? Well, it varies from state to state, from country to country, from province to province. But the good engineering practice is typically to have a power factor above 90%. That's kind of, let's say, the norm or the basic requirement. And after that, well, it will reduce utility bills when you're penalized for it. Another thing, correcting power factor will reduce loading on distribution equipment. simply because you reduce the KVA loading. So reduce the current flowing through your distribution equipment, through your transformer, cable, and so forth. That may sound silly a bit, but let's say your transformer is fully loaded, you want to add some load, but you know you have a poor power factor. Well, correct your power factor, then you can add more load to this existing transformer without having to have a big retrofit in your facility. Another benefit is that as current flow through the network impedance, it creates, I square R losses. More current you have flowing in your network, more losses you have. Correcting power factor will reduces those losses. Typically, in installation, you have 3 to 5% of losses. If you correct power factor, usually you can reduce those losses by 1 or 2%. Not extreme, but it's still a benefit. And obviously, if you reduce losses, you also have an impact on carbon emission. And that's actuality today. Most people want to have a good view and green image. So if you say you're reducing carbon emission, it's a good benefit for most customers. And last but not least, often, power factor correction is used to sustain or support your voltage in your network. And this we'll discuss in more details in the slide to come, so I won't talk too much about it right now. So those are the main benefits of correcting power factor. The most common way to correct power factor is still with power factor correction capacitor, AC capacitor that we installed on the network. If you want to know how much, let's say, kiloVAR, capacitive kiloVAR you need to add on your network, you can use this formula that's in yellow at the bottom of the screen, where you would enter your total kilowatt of your, let's say, on that particular distribution transformer, you would put your present power factor, in this case, let's say 80%, 0.8, and you would put your desired power factor, 0.95, and you compute this, it will tell you, okay, in this network, you would need 42 kiloVAR to correct the power factor from 80% to 95%. And you can see by adding a 42 kiloVAR capacitor, you reduce your KVA demand from 125 kVA to 105 kVA. And that's because the reactive power, instead of being supplied by the source, it's now supplied by the capacitor. Now looking at some power flow, what is indicated here is actually the two types of power. We have real power in green, so your kilowatts, and your reactive power in red, in kilovars. When you don't have power factor correction in your network, well, your high voltage bus, medium voltage bus, and your low voltage bus has to carry both type of power and an increase apparent power. So the impact of this, you can have a power factor penalty, you have no voltage regulation, increased I2R losses, CO2 emission, and no low voltage or medium voltage offloading of your distribution. If you install a medium voltage capacitor bank, so typically medium or large size customer, let's say 5 megawatts or more, typically they would consider this because it's a bit more cost effective for a large plant. The reduction is only seen at the node, at the medium voltage bus. So the benefit is upstream. Your low voltage still needs to carry the real power and apparent power still. So there's still gain to be made here. But you can eliminate the power factor penalty and improve your bus regulation on your medium voltage and high voltage. But the one that benefits the most is the utility typically at this point. If we go back in time, so that's why I call it evolution of power factor correction. 30, 40 years ago, the common practice was to use fixed capacitor to correct power factor. You would have a fixed capacitor on the bus or a fixed capacitor mounted directly at the motor terminals. Not a bad practice. If you still do this, that's fine. Typically, you don't want VFD on the same bus though, because the harmonic generated by these VFD would be absorbed by the capacitor and likely fail prematurely if it absorbs too much. we would limit the KVAR capacity to 15% of the transformer capacity. So that would mean put a 150 kVA KVAR capacitor on a 1000 kVA transformer, for example. But if you don't have much non-linear load in the system, you have a couple of motor that's creating poor power factor, then to put correction fixed capacitor on the motor, it's not a bad practice still today. What is more commonly used now are automatic capacitor bank. I will tell you a bit more about them in the next slide, but they're installed typically on the low voltage bus level, and they're there and compensate for multiple loads on one transformer. It's easier to maintain, it's easier to target if there's issue with them, and it's more cost effective to correct power factor this way. So that way you offload the entire distribution, let's say network at the low voltage level. So not only the medium voltage bus benefit and a high voltage, but also the low voltage bus benefits for this power factor correction. You still eliminate the power factor penalty. You have good I-square losses reduction. You have good voltage regulation in your network. What's inside an automatic capacitor bank? Typically, while these banks are connected in parallel with the rest of the load, you would have a system of bus, multiple capacitor step. Each step would have an overcurrent, and when you have a step protection with a breaker, you also have overload protection. You would have an electromechanical contactor and your capacitor. Then you would have a power factor relay, a controller. The controller takes a reference in voltage, takes a reference in current from the main bus, determine the phase angle between the two, and with this it determines how many steps it needs to energize to meet the target power factor requirement of the customer based on the load magnitude that it sees. As the load increases, it turns on more steps. As the load decreases, it's turned them off. So typically, the response time is in the range of 30 to 50 seconds with automatic capacitor system. Another thing that can be done that may sound more obvious or silly, if you happen to have a facility that has need for a lot of speed control, if you have dominant network with mostly variable speed drive, you may not need power factor correction. So that's what is illustrated here. It's a bit extreme because we all have VFDs, but that's what I mean by this. Because the natural power factor is in the range of 95 to 98%. Then there's another issue you have to be concerned about is to control the amount of harmonic being injected by these VFDs. So it becomes more of a harmonic filtering issue than power factor correction at that point. And in some facilities where you have like large motors, I've seen that in a cement factory, you may encounter synchronous motors, and you can control their field and also control the current it draws. It can actually draw inductive current or capacitive current. So if you have field control, you can actually get your motor to draw capacitive current, so you can use it to correct power factor on your network as well. So it's rarely done, but if you have a few big motors that are synchronous motor, you could do it to correct power factor on your network. At medium voltage, especially at utility level, like high power application, you have synchronous condensers, and that's what they do. They change the excitation of the motor to control the power factor on the network. So one thing that affects power factor correction capacitors are high frequency current and a high frequency voltage, and they're referred to as harmonics. So just a little reminder what harmonics are. Well, harmonics are integral multiples of the fundamental frequency that when added together result in distorted waveform. If we look at this white waveform here, we see it's composed of multiple frequencies. So the blue is our power frequency in North America is our 60 hertz. But there's also other frequency in this wide waveform. By doing the fast Fourier transformation, we can figure that out. But you see that we have third harmonic order, which is 3 times 60 hertz, so 180 hertz, and we have fifth harmonic order, which is 300 hertz, and we also have seventh harmonic order, which is 420 hertz. So those are high frequency being created by non-linear load, or being drawn by non-linear load. Typically, the utility feeds us or gives us a pretty clean voltage source, but as these non-linear current and non-linear load draw non-linear current, rich and harmonic, well, they create distortion inside our facility, and also because they're injected back on the grid, you can also distort the grid. So that's why you have limits in harmonic injection as per the IEEE 519. A few examples here of non-linear load. One that we all use, switch mode power supply. So that's the power supply that converts from AC to DC for our laptop computer or desktop computer. That's on the left. In the middle, we have CFL light or LED lights that are more and more common. And on the right, we have a typical, 6-pulse PWM drive that are commonly found in industry or even HVAC for motor controls. As far as level of harmonic injection of these devices, it varies. Now, let's say switch mode power supply or CFL light and the LED lights, if they have built-in filters, their injection is much less. So typically, these devices are a bit more expensive. And same thing with variable frequency drive. You have different technology that inject more or less harmonic. This one has no line reactor DC bus choke, so your THDI is in the range of 100 to 125%, which is high, but again, you put a line reactor on this and your THDI drop to 40%, so it's always a good practice. To remember, as these harmonic current flow through our network impedance, they create voltage drop at the same frequency. So Ohm law applies. So if you want to reduce voltage distortion, what you do practically in a network is that you reduce the amount of current distortion that flows through your network. So that's how, let's say, filtering function. You can obviously change the impedance of your network, but this is not very practical. So that would mean you would go from a 1,000 kVA transformer and you would increase it to a 2,000 kVA transformer. So typically what is done is that you reduce the amount of harmonic current flowing through your network. By doing so, you correct THDI and you also correct THDV on your network. Now coming to capacitors. Well, capacitor, interestingly enough, are low impedance to high frequency to harmonics. Their impedance is equal, XC is equal to 1 over 2 pi FC. So as the frequency increase, well, the impedance decrease, so they can absorb harmonic current. And that's one of the reasons why they are affected when you have variable frequency drive on the network. So on this diagram here, on the right, we have a 6-pole VFD. The normal flow for the current, it's to go back to the power source, that the power frequency and the harmonic frequency. But if you have capacitors, well, some of these current can start to be diverted and sink into the capacitor. Well, capacitors are typically overrated and they can absorb some harmonic current. But if they absorb too much, well, you will, get them, they will overheat and fail prematurely. So instead of lasting 15 years, they may last 1 year, 2 years, 3 years. So if you constantly failing capacitor, one of the reasons could be because of harmonic. Other factor influence capacitor as like temperature, voltage transient, and the amount of time you switch them on and off. But one of the points you should be looking at if you're failing power factor correction capacitor is how much harmonic you have in your network. And then you can actually have a worse scenario where a standard capacitor bank create resonance in your network. It can actually, well, in a series resonant condition, bring in harmonics from the utility into your facility, or if it's in a parallel condition, you can actually magnify harmonic. So I will try to explain that for you in the next few slides. So the first one we're looking at is what is known as series resonance. And that's a concept that most of us use every day. Let's say in your car, what you have an antenna, which is actually an inductor. And inside your radio, you have adjustable capacitors. So when you want to listen to your favorite radio frequency, you actually tune those two elements so that, in fact, cancel one another, so create a very, very low impedance to that frequency. You capture that radio frequency, amplify it, and listen to your favorite radio station. And in an electrical distribution network, the same thing can actually happen. Your supply transformer has a big inductance. Let's say your 1000 kVA transformer feeding a particular distribution bus. So that's an L. And if you have a standard capacitor bank in your network, well, there is your C. And at a certain frequency, those two impedances will cancel one another and create a very, very low impedance path. I've seen a situation in Canada where a customer added, well, he had a 1500 kVA transformer. He added an induction furnace, and the induction furnace came with a capacitor bank, standard capacitor bank. His facility was not generating harmonics, but because the two element, his supply transformer and his capacitor, were tuning at the third harmonic order, well, it was actually drawing harmonic from utility inside his plant, and then the capacitor will fail within days. And then, okay, things will stop. He would replace the capacitor, and then it will start failing again, basically because he was changing the frequency. So anyway, we get involved and we propose what we call detune type capacitor bank, which I will present in the next few slides, and that resolved the issue. So this is known as series resonance. Now, when you look at the same type of scenario, you have your supply transformer, you have a standard capacitor bank in your network, and you have harmonic generating loads, let's say a rectifier or a DC drive or a VFD. And when you draw this equivalent circuit viewed from the inside your facility, it gives you this equivalent circuit. So this is create what we call parallel resonance. So you have your inductor coming from your supply transformer, you have your capacitor coming from your capacitor bank, and then you have in parallel your nonlinear load. So if you want to calculate, in this case, the resonant frequency, and the same formula applies for series resonance, you can calculate it. You have a 1500 kVA transformer, a 225 kilowatt capacitor bank, and the impedance of your transformer is 5.5%. You compute this, it tells you, okay, you'll be resonating at 660 hertz, which is equivalent to the 11th harmonic order. Okay, so what does that mean? Well, I'll try to show it to you in the next few slides. Now remember, as harmonic current flow through the network impedance, they create voltage drop at the same frequency. What we just did there is increase the network impedance. So we excite, you know, the parallel resonant point, the current flows through an increase in impedance, so we increase the voltage distortion, which in turn increase the current distortion, and then you end up with a high oscillating current between your supply transformer and your capacitor bank. So typically you would trip a breaker, blow fuses, or fail your capacitor at that point. In worst case, you could trip a main breaker of your main incoming as well. So looking at curves of this, so hopefully it's large enough for you guys. On the horizontal axis, you have the harmonic frequency. On the vertical axis, you have the network impedance. The curve in blue is an impedance of your network without any capacitor bank. So basically driven by your supply transformer. So XL is equal to pi FL, so it increases linearly, you know, as the frequency increase. Obviously, you have some R component in there, but it's just, you know, increase your starting point. And in burgundy, you have this big peak here. When you have parallel resonant point, like I just explained, this one is in around the 5th and 7th harmonic order. You have a big increase in impedance. and that will magnify current and voltage. But here in the bar graph, we have in blue, we have the harmonic before in voltage. So we have third, fifth, 7, 11, 13, and so forth. And it's from 0 to 12%. That's the scale. In blue, that's without the capacitor bank. And in burgundy, it's with the capacitor bank. So you can see where there is an increase of impedance, the harmonic are being magnified. Here, the big magnification of the fifth and seventh harmonic order. And again, remember that standard 6-pulse PWM generate mostly 5th, 7, 11, and 13 harmonic order. So that's why there's a lot of harmonic to magnify here. So obviously, capacitor bank manufacturer had to find a solution to this, to be able to correct power factor in harmonic-rich network. And we use the concept of series resonance to control the resonant point. So we put an inductor in series with our capacitor to force the resonant point below the dominant harmonic in our network. Typically in three-phase network, 95% of the time your dominant harmonic would be the fifth. So you'll find that most manufacturers tune below the fifth harmonic order. And we refer to it to 4.2 harmonic order, or 4.2 per unit harmonic. So it's just below the fifth harmonic order. And the parallel resonant point falls between the third and the fourth harmonic, but in three-phase, there is not much third and fourth, so there is no harmonic to magnify. And you have the curve here, typical of detune capacitor stage. Then here the scale has changed a bit, but it's 0 to 3 or 4%, I believe. But in blue, that's without the capacitor bank. And in burgundy, it's with the capacitor bank. And instead of having harmonic magnification, we actually reduce them with the use of detune reactors. So the capacitor bank itself, it's very much like we saw earlier. Very same concept, except we add a tuning reactor in series with our capacitor to control the resonant point of each stage so they don't magnify harmonic on the network. And the tuning reactor is three-phase and resemble something like shown here on the picture. Now, there's also some capacitor bank that are switched, instead of it being switched, having step switch with electromechanical contactor, they may be switched with solid state contactor, which are made of diodes and SERs. The advantage of this is that they switch at the zero crossing and they reduce the inrush current of a capacitor. Remember, a capacitor is a very low impedance when it's first energized, and it will draw high current, high inrush current. In standard capacitor bank, typically we have pre-charged resistor on the contactor to reduce this inrush current. With detune cap bank, the large tuning reactor reduces this inrush current. Typically, in most applications, it's sufficient. But when you have very sensitive network, let's say hospital or airport, and you want to make sure there is no transient, switching transient whatsoever, then you can use solid state switch like this to switch your capacitor stages to reduce the inrush current. Now, as I mentioned, you can use capacitor to regulate voltage on your network, and that brings us to flicker. What is flicker? Well, flicker is a variation of the voltage envelope. And when it repeats itself in time, it can create flicker. It's measured typically in short-term flicker or long-term flicker, so PST or PLT. And typically, it is created by large inductive load that have big variation of inductive reactive power on the network. A good example, spot welder, you see that in the automotive industry quite a lot, and I will show you a good example of that. Ball mill crusher, because you have variation of torque on your motor, or steel shredder, same thing. When you have torque variation, it draws more inductive reactive power during this torque variation, and which make the voltage sag. Another example is, it can be as simple as large motor starting as well. Most of the inrush current of a motor start is inductive, And if you compensate that, you can support the voltage during the motor start with a real-time capacitor bank, what we call it. Here, a specialized device that we use to do this, to be able to compensate power factor in real time, is what we call HVC, so hybrid VAR compensator, which is a mix of active harmonic filter operating in power factor mode only with a detune type capacitor bank. The concept of this is that what we want ultimately is to have the power source supply 0 VARs, inductive or capacitive. And the demand in inductive VAR is highlighted in pink here. At the start, when there's no reactive demand from the load, well, we have a fixed capacitor bank that inject, fixed amount of capacitive reactive power in the network. And then we have a active harmonic filter that has the ability to inject leading or lagging VARs. So when there's no demand of VARs, the active harmonic filter inject inductive VAR to cancel the effect of the capacitor bank. As the demand in VAR doubles from the load, the active harmonic filter just sits idle, and all the reactive power is supplied by the capacitor bank. And then if we see that the demand in inductive VAR doubles from the load, then the active harmonic filter switch and go inject, reactive power along with the capacitor bank to support the need of this load. And ultimately, again, what you want is to have the source supply almost 0 kiloVAR on the network. So an example here that we see in automotive quite a bit is a welding line. We have multiple welders. So you have your supply transformer, you have all your welders operating in parallel, and then you put your compensating system here in parallel. So the key here is to remember is that this system can inject capacitive reactive power within 5 milliseconds, within a quarter of a cycle. Welders weld typically between 8 to 16 cycles, electrical cycles, so it's very fast. It turns on very fast and turns off very fast. So you cannot compensate this load with a fixed capacitor or automatic capacitor bank. They're not fast enough. You will basically actually magnify the flicker if you try to do it this way. So you need to be able to turn on and turn off the capacitor very fast to compensate for these type of rapidly fluctuating load. So looking at this example, we have the power factor at the top, varies from 50% to 75%. The voltage supply varying from 450 volt to 500 volt. The demanding current varying from 300 amp peaking at 3000 amp. Kilowatt demand varying up to 1000 kilowatt. KVAR going up to about 1700 kiloVAR, and the KVA going to about 1800 KVA. Now to note on this trend plot, it's only 20 seconds. So there's 22 minutes, 20 seconds, and 22 minutes, 40 seconds. So all these peaks are coming very, very fast. And if you look closely, the peak in current happen when you have a high demand of inductive reactive power right here. And this is inductive. So when we turn on the capacitors, what we're targeting is these peak of reactive power to eliminate those. By doing that, we'll reduce apparent power as well. So that's with the system off. And when we turn on the system, the power factor is maintained near unity, voltage regulated at about 490 volts. Current drops in the range of 1000 amp, sometimes some peak to 1500 amp, but instead of 3000 amp is much improved. Kilowatt remains unchanged. The big change is that is in inductive reactive power, which would oscillate between plus or minus 100 kVAR. And then the KVA, instead of peaking at 1800 kVA, you're peaking at about 800 or 900 kVA. So big improvement, like a 50% improvement in KVA reduction in your system. By doing so, we reduce the voltage sag. By reducing the voltage sag, we reduce flicker directly. And on top of that, on the welding line like this, you improve throughput for the production, and you improve the welding quality as well. And next, it's a little bit about the future. What's coming down the pipe from various manufacturers. What we've seen is that active harmonic filters have evolved. They can obviously mitigate harmonic. They can also correct power factor in real time and do load balancing. So the idea of manufacturer is actually bring this idea to low voltage compensation. And what they're doing, they're using power electronics. It's basically IGBT with a DC bus. It's very similar technology as solar inverter or UPS, but used to inject reactive current and negative and zero sequence current to rebalance the current on the network. So you have your IGBT switching, which is pulse width modulation. It's being filtered or cleaned up by our internal filter, and what you inject is this current waveform on the network. And that you can have balancing current in this waveform, and also leading or lagging bars that you can inject. And what's inside these devices? Again, it's very much resemble of, UPS or solar inverter or drive. So you have a DC bus at the top. Typically, you would have an ANC filter. We commute the IGBTs at very high frequency, typically in the range of 20 kilohertz, but we don't want this 20 kilohertz to get out into the customer network. So we filter it internally with this LCL filter here to have a nice clean current that we inject into the network. Here's a contactor. Typically, when you start this device, you pre-charge them through soft charge resistor to charge the DC bus. Once that's done, and you close the contactor to a full conduction. Then you would have typically forced air ventilation. You would have air drawn from the front and exhausted through the back. And then you would have your power electronics, which is insulated gated bipolar transistors, which are connected to heat sink, and you have air flowing through heat sink to cool them off. And then to interact with the device, you would have a human machine interface. And nowadays, most of the time, it's a touchscreen display that is utilized for that. And then you would have some, printed circuit board for control and connection and so forth, and communication. So the advantage of this, well, you eliminate the possibility of resonance. There's no more issue of resonance that disappears. You can inject leading or lagging bar in the system, so you can correct for leading power factor or lagging power factor both ways. You can inject VARs per individual phase, so it's very, very precise. You have infinite kilovar resolution, so instead of having you're turning up step in the system, you can basically track at plus or minus 5 kilovar, so excellent resolution in the system. And you can inject real-time bar injection, so you can use this device to correct flicker, to support the voltage in your network, or let's say you have a motor starting often and you need to support the voltage. Well, you can use this type of device to do it. And on top of that, because you have individual phase injection, you can actually rebalance the current on the network. So that's what is shown here at the bottom. So you have an unbalanced current, phase 1, 2, and 3, and once you turn it on, you rebalance your current on your network. By rebalancing the current, you also rebalance your voltage supply. Big advantage, well, it's the resolution. That's what I try to highlight here. So here we have a small load, 400 kilowatt load from 84% just above power factor, and we want to correct it to unity. Well, with a 25 KVAR capacitor bank, which is rare, typically would be more like 50 or 100 kilovar steps, you see the step that it takes, to regulate. But you would do the same thing, same compensation with an EVC system. Well, you would track perfectly the KVAR needs of this load, and you could basically, if it's sized appropriately, you could basically maintain unity power factor at all time. So to finish with our power flow, so if you use this type of device, on all your distribution, it's kind of ideal power factor, you could maintain it to unity. You would have, like, say, basically 0 kiloVAR supplied by your high voltage bus, medium voltage bus, and low voltage bus. So you would have power factor penalty elimination, optimal voltage regulation, let's say best I-square losses reduction and CO2 emission, and best, load balancing and let's say voltage regulation in your network. So manufacturers are working on this to reduce the costs, and because of economy of volume, we're getting there, and also because the power electronics are more and more affordable, then we're going this way for power factor correction moving forward on low voltage. A little bit matching what has been done at medium voltage for let's say large distribution or steel industry or hard furnace where they use STATCOM. It's very similar, but done on low voltage network. That's it from me for the presentation. Now we'll pass it back to Amara for question, and I'll do my best to answer them.
Excellent. Thank you so much, Remy. Now, Remy Bolduc with Schneider Electric will answer questions from the audience. Please type your question for Remy in the Ask a Question box on your screen, and we'll get to as many questions as time allows. Questions that we don't get to today will be posted online at www.csemag.com. That's csemag.com. It will be with the archived version of this webcast. And remember to download a certificate of completion or a copy of this presentation. Use the Event Resources tab on the left side of your screen. All right, Remy, we have quite a few questions here. Let's take these first couple. Why use power factor correction in low voltage networks?
Well, thank you for the question, first of all. Well, the first, typically, most of the times, it's to eliminate utility power factor penalty. But if doing it at low voltage, that's where you have optimum compensation, because you reduce your losses throughout your system, and also improve how much power you can supply by that distribution, because you reduce apparent power from the low voltage distribution. And I've seen in the example there, that I showed earlier, we had a reduction of 20 kVA. Well, you can then use the space to add more loads in your system and use your system at its full capacity instead of using it at poor capacity at 40, 50, or 60%. Then you can use it at 100% capacity and keep adding load, and that avoids the customer to add more distribution, more transformer, and more switchgear, and so forth. And you have the added benefit of reducing losses and CO2 emission, and a very good voltage regulation for all your load that are supplied by this distribution.
Okay, got it. Thank you. Next question for you. Why is it almost predictable that condensers will blow up in installations with VFDs?
Yeah, so we touch on this, so that's a very good question, very much aligned with this presentation. But we've seen variable frequency drive generate high frequency current, harmonics, and naturally capacitors are low impedance to these high frequency, so they will sink some of these high frequency current, and it makes them overheat because of the additional RMS current, and also the voltage distortion stress their dielectric, their insulation, and they will break down quicker, so affect their life expectancy. So instead of, again, lasting 15 years, maybe they'll last 6 months or a year. And in very severe application, if you have resonance, parallel resonance, and harmonic amplification occurring, well, this degradation and this current flow is increased, and then you may have capacitor failing within days or within weeks of installation. That's why.
Got it. Thank you. All right. Next question, Remy. What kind of products are available when the electrical installation or a building has a leading power factor?
Good question. Let's say if we go back in time, in the old days, 25, 30 years ago, making me feel old, but anyway, they used to use a bank of inductors to inject inductive VAR in a system. But this tends to be abandoned now. What is used today is mostly active harmonic filter that have the ability to inject, leading or lagging VAR in a system that can correct power factor in both direction. And typically this is what is used. And this is particularly critical when you have a backup generator in a facility that does not handle, leading power factor very well. It affects its governor and its control. So I understand the question where it's important to maintain the unity power factor or a lagging power factor to make sure that you can operate your backup generator safely. We've done several applications like this, and in data center we face this where new type of switch mode power supply are compensated to reduce their harmonic. They have a THDI of like 5%, but under low load condition or even at full load condition, they can create leading power factor. And because of the high density that is found in some data center of the switch mode power supply, they can actually create leading power factor on the network. And that creates an issue when they try to switch back to backup generator to keep the data center in operation. So I can see where the question comes from, and it makes sense. So today, the best course of action is to use active harmonic filter to correct the power factor in these situations.
Okay, thanks. Next question. We do have a lot of questions here. So if you have a question for Remy, please type your question into the Ask a Question box on your screen. Next one. What is the best way to determine size and type of power factor correction at a new facility during early design?
In an ideal world, typically, let's say if you have a big installation, you can use, let's say, a software like ETAP to do a power flow study. Then you will determine, your kilowatt, KVA, and KVAR and your power factor up front. But that's for a large installation. I see many consultants, doing their load table with their projected power factor for each load, so they can actually determine what will be the kilowatt and KVA and KVAR and power factor. And from there, we're using the formula I shown earlier in the yellow bar there. You can actually calculate how many KVAR you would install in the facility based on your total kilowatt use and your, let's say, estimated power factor and your desired power factor. And at Schneider Electric, and many manufacturers have that. They also have some simpler simulation software that can assist you at determining what will be your power factor, in a new facility based on the single line diagram. And we can do pretty good estimation from that too. And some people like to use rule of thumbs. In the old days, you would put, let's say, 25 to 30% of the transformer rating. So that would be 250 kVAR or 300 kVAR capacitor bank. Now, because you have more nonlinear load that have good power factor, I would say you could estimate that 20% of your transformer rating for the size of capacitor bank, let's say 200 kVAR, if you want to use a rule of thumb. So you have different approach for different type of projects, but it can be estimated. And many manufacturers can assist with that if need be.
Sure, thank you. This next question is a bit of a follow-up or a clarification to what you just discussed. Can power factor and correction be designed into a new system, or is it an after-the-fact system correction only?
I would say most of the project we face, it's done up front. We call them greenfield. With the software available today and experience from, consultants, specifier, and engineers, typically it's done up front. Afterwards, we all know that during the CAPEX phase, it's easier when you have capital expenditure. It's easier to plan for it. After the fact, it's always much more difficult to have money to correct the power factor in the OPEX phase of the design, let's say. But in today's world, it's relatively easy to design upfront during the design phase of the project.
Okay, good. Thank you. Let's see here. This is a two-part question, Remy, so if you need me to go back, just let me know.
Okay.
What can a design engineer do to limit issues with power factor? And what is the best cost-effective solution for an overall system?
To limit issues nowadays, I would say, well, the most cost-effective, I'll start with the last part, is probably to use automatic capacitor bank with electromechanical contactor. That would be the most cost-effective. And to limit risk, I would say upfront plan to have detuned type capacitor bank in your network, because in most network today, you have non-linear load that will inject harmonic current, and you want to avoid harmonic magnification. So that's today. In the future, like it's coming very fast too, EVC would be the solution. Then there's no risk of harmonic magnification, and they won't be influenced by harmonic, and you will be able to correct, power factor in real time. So that's hopefully that answers the question.
Very good, thank you. It looks like we have time for just one more question, Remy. And this goes back to a little bit of what you discussed earlier. Are data centers or server farms or co-location facilities, whatever you'd like to call them, known for poor power factor or for poor electrical loads?
Poor power factor, or can you repeat?
Yeah.
I missed it. Oh.
So are they known for poor power factor for electrical loads?
Not really, especially, and it varies depending of let's say, the age of the data center as well. Older data center, they may have lower power factor, mostly because of their mechanical load, like chiller load and so forth. And also their switch mode power supply that were older technology that would have like lower power factor. But newer data center, they have these new switch mode power supply. And the one type of load that would have to watch for that could have poor power factor is the chillers and the mechanical load and the pump and fans. That could affect your power factor, but not a great deal. Before, there was a big issue with third harmonic order in the data center, but because of the evolution of switch mode power supply, it's not such a big issue anymore. Usually the TGI is in the range of, 12 to 20% in data center. It's not extreme. But for the mechanical load, then that would be the place that would be looking at in data centers to do either power factor correction or harmonic filtering. That would be the heavy load to watch. But they're not, let's say, as dirty as people would think. They are pretty clean now, especially with the evolution. What we found on the market, engineers tend to do a good job in data centers, and they have learned from the past as well, and they're pretty clean in loads now.
Good. Okay. Well, those were some interesting questions. So thank you for asking those questions. And thank you, Remy Bolduc, for an incredible presentation. I really appreciate your time and expertise today.
Well, thank you very much for listening to me, guys.
Yes. And I'd also like to extend a special thank you to our sponsor, Schneider Electric, for supporting today's event. And now that we are just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it. We do use this information to improve future events. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, I'd like to thank you for attending. This now concludes our webcast. Thank you and goodbye.